Welcome to our video presentation on the mechanical design and analysis of the post-mounting bracket project. We are from Group 19, consisting of Wei Zihao, the group leaders, Su Junheng, Tan Ming, and myself, Tang. So, our presentation video will cover the following topics: introduction, methodology, results, discussion, and conclusion. Let's begin it with a brief overview of our project. On the left side, you can see that basic design criteria of the post-mounting bracket. The key requirements of this bracket are as follows. It should be made of metallic material capable of withstanding a minimum load of 300 newtons, weighing less than 700 grams, and having a factor of safety greater than 2. And finally, exhibiting deflection lower than 0.8 millimeters. These are the objectives of our project in each phase. So, the main objective is to develop the ability to analyze three-dimensional mechanical structures using linear static analysis, thermal stress analysis, and free vibration analysis. Next, we have the flowchart outlining the entire project. In the first phase, we gather information from the project briefing sections. And after studying the criteria and requirements, we proceed to generate our design concept and translate it into a CAD model. Subsequently, we perform linear analysis using the model to ensure that our design met the specific requirements. Once this was accomplished, we proceed with the remaining analysis and compile our result and discussion. Moving to our first design, it was inspired by a design of load hanger. First design met all the project requirements, but it fell short in terms of weight. To address this, we decided to reduce the weight by hollowing out the bar. This successfully achieving a weight reduction without significantly affecting the other requirements. However, the weight was still slightly above the target. Consequently, we arrived at our third design by incorporating a kite-shaped hole at the center of the bar and thinning the bar. This final design not only met all the requirements but also yielded outstanding results.
I am with how next I will present the result and discussion. In this project, we have done three analyses. We are linear static analysis, thermal stress analysis, and free vibration analysis. So I will begin the first section, linear static analysis. The site has shown equivalent stress result. From the diagram, it can know that the maximum stress is 71.75 megapascal. It is labeled by the color red. So it is located at the left side of hallway, where it is set by for speed support for our this product. So this maximum stress, of course, may be due to there being a tensile stress between the feed location and the load applied, in which the feed location is applied for to the direction the less, while the load applied is to another direction. Following, the site has shown the total deformation result. From the diagram, it can note that the maximum deformation is 0.1844 mm. It is labeled by color red. So the maximum deformation is located at the right side of the hole, where used to handle the 100 Newton post. This situation may occur due to it is the location of load applied and it is the fast distance with the feed support. So from this project, it can find that we are frequent to calculate the FOS, which is method of safety, and required to achieve FOS greater than 2. So what is important? First, FOS can understand the yield criteria whether a low or high tendency of field. When FOS less than 1, it means the product has high tendency of field loss. And other way, more than 1, the product has low tendency of field loss. So besides, FOS can explain how much stronger of a system. The higher of FOS means the system can build a higher of stress. So the last one is material selection. As we know, FOS calculation is depend on the material yield strength and the maximum stress. If FOS calculated too high, the designer can choose another suitable material to set the cost.
Hi, my name is MING. My normal matrix is 211-400-870. So I will continue my part. So we can see that without thermal change, the maximum value of the equivalent stress result is 71.65 MPa. This value represents the highest stress experienced by any point in the structures. Next, the minimum equivalent stress is 0.053492 MPa, so the lowest stress experienced by any point in the structures. So in thermal change, the maximum equivalent stress increased to 75.251 MPa, while the minimum equivalent stress increased to 0.10405 MPa. This finding implies the bracket structures stress levels increase as a result of the introduction of thermal change. So the material that we use is titanium alloy, and the yield strength that given is 930 MPa. So without the thermal change, the FOS that we get is 12.98. With thermal change, the FOS that we get is 12.36. So both values are interpreted as low tendency of values because it's larger than 1. So in terms of tendency of bracket value, the bracket without thermal change will be more safety compared to the bracket with thermal change. So for total deformation result, the highest overall deformations measured in the bracket without thermal change was 0.18444 mm. The minimum overall deformations was 0 mm. The highest total deformation stayed nearly the same in analysis with thermal change at 0.18483 mm, while the minimum total deformations remained at 0 mm. This finding implied that the general deformations behavior of the bracket was not highly affected by the heat change. So the first reason of the different result due to the temperature effect is material properties. The titanium that we use has a low coefficient of linear thermal expansions. So the deformations really change due to the temperature effect. And the second reason is boundary conditions. The thermal conditions will impact the temperature, thereby influencing the distributions and assessments of stress and deformations. So that's all for me. I will pass the presentations for Susan.
Good morning, I'm Su Heng. I would like to share you the result and discussion for vibration analysis. So the higher total deformation indicates the largest displacement. So the natural frequency is slightly increased from the different mode shapes, with the motion belong to X, Y, and Z directions, showing the elastic structures. Next, do you know natural frequency is the frequency at which a system tends to oscillate in the absence of any driving or damping force, which means that it vibrates without any external force. So the importance of natural frequency is to identify the points of irreparable damage due to increased vibration amplitudes, prevent the resonance which can lead to structural problems, and optimize problems to ensure structural stability and integrity. Before we end, let's see our conclusion. Overall, the objectives of project were achieved. So for the linear static analysis, so it is successful with the project requirements that shown below. So for the thermal stress analysis, it is slightly increased on the solution results about the impacting the thermal change. And for free vibration analysis, it's providing a valuable insights into the frequencies and mode shapes of the bracket's vibrations. What's the factor that can influence the results? So the first one is the thickness of the plates, where the fixed surface is located, affect the stress distributions. And the second one is the width and the thickness of the bar, then connecting with the cylinder with the load on the fixed plate. So for suggestions, is mesh generation environment and the material properties and constitutive models. So anything need to be careful for the meshing and the material sections to enhance the accuracy of the FEA simulations. Anyway, thank you for lending your ear to our presentation. See you. Bye.